Hi, this is Chuck. In this particular video, we are going to take a look at a technique known as variation of parameters. It's also called the Lagrange method. You should have already taken a look at the method of undetermined coefficients. That works for second order non-homogeneous equations that are linear. And it works for special right-hand sides. There were a couple of cases where it'll work, and we've hopefully gone through that. If you haven't seen that already, you may want to review that video first. But what we're going to take a look at here is what happens if you don't have one of those special right-hand sides. Well, as with the previous method of undetermined coefficients, we're going to start with a second order linear non-homogeneous differential equation, which is right there. Now, one of the things I want to point out to you, and this is important, notice that the coefficient on the y double prime is 1. If it's not 1, divide by whatever is there now to create an equation in this form. When we go about solving this, what we're first going to do is to solve the homogeneous case, where the right-hand side is 0. This will allow us to then obtain two solutions, y1 and y2, and remember the Wronskian of these two solutions is never 0. If it is 0, that means that y1 and y2 are scalar multiples of one another. So if one solution is x, the other is 3x, and that's not going to work. I've provided for you here the definition of the Wronskian. It is the determinant, which is where you take the diagonals on this direction minus the product of the diagonals in that direction. And for a 2 by 2 matrix, it gives you the determinant. And this does verify the linear independence of our two solutions. Once we obtain our complementary solution, we're going to go after a particular solution. This is where things vary from techniques you may have seen earlier. What we're going to do is we're going to introduce a coefficient on our y1. Remember, y1 is one of our solutions from the homogeneous solution. And we're going to introduce a second function, u2 times y2. Okay, and this is going to be our particular solution. Now, it's important to notice here that u1 and u2 can be functions of x. They don't have to just be things like 3, 4, -7. They can be things like x e to the x or x cosine x, things of that nature. When we take the derivative of this equation on the top line, we obtain, using the product rule, first these two terms. Secondly, we obtain these two terms using the product rule on the second term in the top line. It's always going to be the case that the u1 prime y1 plus u2 prime y2 is 0, which then allows us to simplify our particular solution's derivative, y prime of p, to u1 y1 prime plus u2 y2 prime. When we have this, we can now go ahead and compute the second derivative of our particular solution. Since u1 is assumed to be a function in terms of x, we're going to need to use the product rule here, which will give us these two terms. And the same thing will be true of u2. u2 is going to be a function of x, and we're going to need to use the product rule there, which will give us those two terms. Once you have these terms computed, we're going to substitute yp prime and yp double prime, the particular solution's first and second derivative, into the original equation. And this will give us something like what's on this next line here. Notice I have my right-hand side, the g of x, way over on the left. Okay, so it's way over here. I haven't left it out. It's still in there. And you get a bunch of terms. Now, notice as well that this first grouping of terms is from the y double prime. If you recall back to equation 1 up at the top, we had p of x times y prime. Well, here are our y prime terms, and you have to multiply them times whatever this function is times y prime. The same thing holds for the third term here. We're going to have our y terms, which is going to be u1 y1 plus u2 y2. Remember, that is our particular solution that we're looking for. And it needs to be multiplied by that coefficient q of x. Depending on what these functions are, p of x and q of x, this can get a little entertaining on the algebra. Once we distribute the p of x and the q of x times the appropriate terms, we can regroup. We can go through this equation up here at the top of the screen and regroup, looking for all of the terms that have a factor of u1. And when you bring together all the terms with a factor of u1 and factor those out, what we wind up with, this is pretty cool. We get y1 double prime plus p of x y1 prime plus q of x y1. Secondly, using this equation at the top of the screen, when we bring together all of the terms that have a factor of u2 of x, we obtain this second term. Factoring out the u2 of x, we get a y double prime plus p of x y prime plus q of x y. And notice these are all the y2 terms. And remember, y2 is a solution. Just like in the first term over here, y1 is a solution, which means that both of these top terms are equal to 0 because y1 and y2 are solutions to that equation, each case, in the brackets. So what we're left with, after we have regrouped everything and identified that the first two terms are 0, we're left with this. This is actually the equation right there. This gives us one of two equations that we're going to need to use. The second equation is this u1 prime y1 plus u2 prime y2 equals 0. This is something that we ran into earlier. Okay, up the road here a little bit. Here it is. Okay, so we have that equal to 0. Now this gives us then two equations. We have a system of equations right here. What we're going to do is solve this system of equations for either y1 or u1 prime or u2 prime, and then substitute to get the other of the u solutions. In this case, it'll give us u1 prime equals something and u2 prime equals something, and then we need to integrate both of them, and ta-da, we're done. And that's all there is to this variation of parameters. You may say, yeah. Let's slow that down and see how this really works. We're going to take a look at several examples here, and then we're going to finish up with a quick review of dealing with things that require the method of undetermined coefficients as well as this variation of parameters. But first, let's take a look at several examples, and we're going to solve this using the variation of parameters technique. This is not to say that this is the only approach that'll work in all cases. In our first example here, where we have y double prime plus 3y prime plus 2y equals e to the x, we could have solved this the old-fashioned way. And in fact, on the left-hand side of the screen, let's work through that. Since it is a second derivative, okay, or a second order equation, we can solve the homogeneous equation using the quadratic formula, and this gives us our two solutions. y1 equals e to the negative x, and y2 equals e to the negative 2x. Recall this comes from our roots, r equals negative 1 and r equals negative 2. So those two roots there give us that particular solution, or not particular, that complementary solution. Now that we have this, we can go after the particular solution. Remember, the right-hand side is e to the x all the way up at the top. This is one of those special cases. So what we can do is we can identify our particular solution, y of p, as a times e to the x. Computing the derivative, we get a e to the x, and computing the second derivative, we get a e to the x. Well, that's pretty easy. We're going to substitute these now into the equation at the top of the screen for y double prime, y prime, and y. On the y double prime, we're going to have our a e to the x. Then we have plus 3 times y prime. Well, that's a e to the x plus 2 times y. Well, that's a e to the x equals e to the x. On the left-hand side, they're all going to add up, and we're going to get 6a e to the x equals e to the x. You can divide both sides by e to the x because you know e to the x is never 0, so we don't have to worry about dividing by 0. And this gives us that 6a equals 1, or a equals 1/6. This gives us then our particular solution right there as 1/6 e to the x. Remember, our general solution can be created. So if you ask for the general solution, you have to pay attention to what you're being asked for. Okay, the general solution is going to wind up being the y complementary plus the particular. But that's easy enough to do. The complementary is all the way at the top of the screen in the left-hand corner, and the particular solution's right there. Adding those two together, you have a general solution. All right, so we can see here how to go about solving this using methods you should be familiar with at this point. We're going to go back through this exact same problem, and this time we're going to use variation of parameters. Truthfully, would I choose variation of parameters as my first method of solution for this particular equation? No. It's a little more involved. As you can see on the method on the left, that went pretty smoothly. Not a whole lot there to get hung up with. But because things work smoothly, we're going to try it with this variation of parameters as a first run through for you. Okay, so this will give you a chance to practice some. Okay, so suppose we had not solved our problem, that one at the top of the screen now, using the method of undetermined coefficients. We're just thinking, I'm going to do the Lagrange method. Okay. As with the other earlier method, we're still going to solve the homogeneous solution. We get the same two solutions. y1 equals e to the negative x, y2 equals e to the negative 2x. This is where things change up a bit. Using the variation of parameters technique, we're going to use these two equations right there, recalling that u1 and u2 are both functions of x. Okay, so in the first equation, we're going to have u1 prime times y1. Well, y1 is this e to the negative x, plus u2 prime times y2, which is e to the negative 2x, equals 0. So there's our homogeneous solution. Then we're going to use the second equation right there. It's going to be u1 prime times y1 prime. Now be careful. y1 prime is going to be a negative e to the negative x. And you can see I have the negative times the u1 prime, e to the negative x. Then the second term says u2 prime times y2 prime. Well, that's going to be a negative 2. We've got the negative 2 e to the negative 2x. So we have everything accounted for there. We now have our system of solutions. For this particular solution, notice that the first terms are the negative of one another, which is great because that allows us to just add our two equations together. The first terms, the u1 prime e to the negative x, will subtract off. And what we're left with is u2 prime e to the negative 2x minus 2u2 prime e to the negative 2x, which gives us just a negative u2 e to the negative 2x. Well, I need to first solve for this u2 prime. So I'm going to multiply both sides by e to the 2x, which on the right side will give us e to the 3x. And we have a negative, move this up to the top, we have a negative u2 prime equals this e to the 3x. I need to do two things. First, I'm going to multiply by a negative, which will give me a negative e to the 3x on the right side. And I don't want the derivative, so I need to do the antiderivative or integrate it. This gives us then our second line right here, where we have u2 is going to be negative the integral e to the 3x, which is a negative 1/3 e to the 3x. Now that we have a value for u2, I'm going to substitute that into either the equations referring to these two equations up here, and I'm going to go with the homogeneous equation. And I have my u2 prime. Well, gosh, u2 prime is up here. It's a negative e to the 3x. So I'm just going to substitute that in there, and it gets multiplied by e to the negative 2x. And when we simplify that, we're going to wind up with these two terms multiplied together to just give us e to the x. Add that to the right-hand side, and we have u1 prime e to the negative x equals e to the x. To isolate u1 prime, I'm going to multiply both sides by e to the x, which will give me u1 prime equals e to the 2x. Integrate that, and we get u1 is 1/2 e to the 2x. All right. Where do we go from here? Well, the next thing is to compute our particular solution. And our particular solution in the method of Lagrange is u1 y1 plus u2 y2. Well, u1 is this 1/2 e to the 2x. Recall from up here when we solved the homogeneous, up at the top of the screen, y1 is e to the negative x. Aha, there's the e to the negative x all the way down at the bottom of the screen. Then we're going to have plus u2. Well, that's going to be a minus 1/3 e to the 3x times my y2 is this e to the negative 2x from way up there at the top of the screen. All right, so let's move on down here a bit. I'll leave it about like that. When we multiply the e to the 2x and the e to the minus x, that gives us e to the x. When we multiply the e to the 3x and the e to the negative 2x, that gives us, once again, e to the x. And look there, you have 1/2 e to the x minus 1/3 e to the x. And what do you know? You wind up with the same solution we got before, where our particular solution is 1/6 e to the x. You get the same thing either way. Okay. Let's tweak that equation that we just looked at, our y double prime plus 3y prime plus 2y, by changing the right-hand side from e to the x to natural log of x. Can that really make that big of a difference? Well, let's take a look. Step one, as earlier, is to solve the homogeneous situation. And the good news is the homogeneous situation is going to have the exact same answer as the previous problem did. So we can move right into step two, where we have our system of equations that we want to solve, these right there. And in place of y1, we're going to put our e to the negative x. In the place of y2, we're going to put our e to the negative 2x, our solutions from the homogeneous equation. Then in the second equation here, I need to compute the derivative of e to the negative x. Well, that's kind of like what we did before. So this is going to wind up being minus u1 prime e to the negative x. And The second term on the left-hand side is going to be this u2 prime times the derivative of e to the negative 2x. That's going to be a negative 2 e to the negative 2x. Notice that the left-hand side of both of these equations is exactly the same as what we did before. No big surprise. The only difference is our right-hand side function is now natural log instead of e to the x. As was the case in the previous one, when we add the two equations together, these leading terms cancel out. And we're now left with a negative u2 prime e to the negative 2x equals natural log of x. Multiply both sides by e to the 2x, trying to isolate the u2 prime, and multiply by a negative, is going to give us a negative e to the 2x natural log of x, which is what you see us attempting to integrate right here to get u2. We're undoing the derivative, the antiderivative. Okay. We can also at this point solve for u1 prime. We substitute it in to the, we take our u2 prime, substitute it in, and I'm going to substitute it into the first one. And when you do that, you wind up with u1 prime is equal to e to the x natural log of x. Okay, so all I did here was I took my u2 prime and I solved for that, which is going to give me that u2 prime is equal to negative e to the 2x. We're running out of space here. Natural log of x. If you substitute that in for the u2 prime there, you can solve and you'll get that u1 prime is going to be e to the x natural log of x. Okay. Notice the differences are it's not a negative, and the exponent on e is now a 1 instead of a 2. Okay, so we have these two derivatives, and to compute u1 and u2, we just compute the antiderivative of each of these. Well, the entertaining part here is we can't do these integrals. Okay, this, as well as this, involves integration techniques that you have not seen yet. Great. If you want to check and see what really happens, you can substitute either of these two into Wolfram alpha, but what you're going to wind up with is something that looks like this. You're going to get e to the x natural log of x minus ei of x, which is an exponential integral or an elliptical integral, whichever you want to call it. What on earth does that mean? Well, that's beyond the scope of this course, that's for sure. So in this case, we can't really solve for u1 and u2 specifically. We're just going to leave them as the integrals. So in this case, we're going to report our particular solution, which is right here, as u1 times y1. And remember our u1, wait a minute, where'd it go? Is just going to be, I'm just at the top of the screen, I'm going to call u1 this integral e to the x natural log of x right there. And the y1 was negative, or e to the negative x, plus the u2 is going to be this negative e to the 2x natural log of x integrated times y2, which is e to the negative 2x. And I'm going to call it done right there. I'm not going to attempt to integrate those. That is way beyond the scope of this course. The general solution winds up being our complementary solution plus the particular solution, which is just going to be the c1 e to the negative x plus c2 e to the negative 2x, along with all this stuff that we've got right here. So the solution winds up getting a little bit longer and involving integrals that you've not had the chance to learn how to tackle yet. So small changes in the equation can lead to very different results as far as the solution. Let's take a look at a third example. In this case, we have y double prime plus y equals tangent of x. If we first solve for the homogeneous equation, as we've done in the previous two, we're going to have r squared plus 1 equals 0. This gives us two complex solutions. Okay, we're going to get 0 plus or minus I. Remember that alpha is your constant term, and beta is defined as the coefficient on the imaginary term. Our complementary solution is defined as C1 e to the alpha cosine beta 1. Say what? That's going to be C1 e to the alpha x cosine of beta x. This should look familiar to you from previous sections. Plus the C2 e to the alpha x sine of beta x. And all I'm going to do is I'm going to substitute in 0 for alpha. Oh, that's kind of nice, because when I substitute in 0, I get e to the 0. Remember, e to the 0 or anything to the 0 is just 1. So this first term simplifies to be C1 cosine x. Using the same substitutions in the second term, we're going to wind up once again with e to the 0x. Our second term simplifies to just be C2 sine x. Now, remember, in our complementary solution, it is C1 times y1 plus C2 times y2. This gives us then that y1 is going to be a cosine of x and y2 is going to be the sine of x. Just a quick reminder as well, g of x is tangent of x. We're heading into step 2. In step 2, recall that we're going to have the two equations that are over here on the left side. We're going to have our u1 prime y1 plus u2 prime y2 equals 0. And our second equation is going to be u1 prime y1 prime u2 prime y2 prime. The sum of those two equals g of x, which is tangent of x in this case. Okay, what on earth do we do with this? Well, substituting in cosine for y1, sine for y2, we get this first equation on the right-hand side. In the second equation, we want y1 prime. Well, the derivative of cosine is negative sine. That gives us our first term here when we substitute in negative sine. We want u2 times y2 prime. Well, recall that y2 is sine, the derivative of sine is cosine. That gives us our second term right there. And in the second case, we're working with the non-homogeneous, so we set it equal to tangent of x. In order to get this to simplify some, we want to add the two equations together and get something to cancel out. I'm going to multiply the first equation by sine of x, which is why I have that sign in yellow. Multiply the second equation by cosine of x, the cosine in yellow. And when you multiply through, we're going to get y1 prime sine times cosine plus y2 prime sine squared equals 0. So that's this equation. Multiplying the second equation by cosine is going to give us this right here. Now, recall quick like, where'd tangent go? Well, tangent is sine over cosine, but if I multiply both sides by cosine, oh yeah, the right-hand side simplifies to just be sine. Notice now the first terms cancel. Those are gone. And what you have is u2 prime times sine squared plus u2 prime times cosine squared. Now, this is really cool because we get u2 prime times cosine squared plus sine squared, which is equal to 1. This gives us u2 prime as sine, and that's pretty straightforward to integrate to get u2 as negative cosine. If we take u2 and we substitute it into either of the equations, and I'm going to take the u2 and actually the u2 prime and substitute it into the first equation. Okay, and that's going to give me this. Okay, when I substitute it in, actually it's going to give me the next line down. I'm going to use the homogeneous equation, substitute in u2 prime, and remember, as you can see at the top of the screen on the right, u2 prime is going to be this sine. Now we're going to have sine times sine squared, which is going to give us sine cubed. Okay, and we're going to have that plus u1 prime cosine times sine equals 0. Move the sine of x cubed to the right-hand side, which gives us negative sine cubed of x. We still have our u1 prime as cosine times sine. To get u1 prime, I'm going to divide both sides by cosine times sine. It's going to give me this. Well, wait a minute, where did the sine cubed go? Well, we had sine cubed, and we divide it by cosine times sine. Oh, a sine cancels. So we have negative sine squared over cosine. Factoring out the negative, remember that sine squared is 1 minus cosine squared over cosine. This can be rewritten as cosine squared of x minus 1 over cosine. Now, this will simplify into cosine squared of x over cosine minus 1 over cosine. You may be wondering where this negative sign went. I distributed it, which gave me a negative 1 and a positive cosine squared, which is what you see over here. Okay, so what I now have is u1 prime is equal to cosine squared over cosine minus 1 over cosine. This first term will simplify to just give me cosine. The second term, well, it's just going to be the 1 over cosine. And because I want u1, not u1 prime, I need to integrate each of these. Integrating the cosine gives me sine. Integrating 1 over cosine, and if you're not quite sure how to do that, you can always just use the integration table that was provided, okay, is going to give us minus, the minus coming from right here, and we're going to have our natural log secant x plus tangent x. This gives us then that u1 is equal to sine of x minus the natural log of secant x plus tangent of x. Okay, so let's move on. To get our particular solution, we want to look at u1, y1 plus u2, y2. u1 is what we just got done computing. It's all of this. y1 is what we got earlier from the homogeneous solution. It's cosine. u2 is what we obtained first off. And the y2 is from the homogeneous. So we now have our particular solution being this. Now, one of the things to notice here is if I multiply stuff out, I'm going to wind up taking this cosine and distribute it times each of these terms. And I'm going to get a cosine x sine of x minus cosine x natural log of all that stuff. And then over here on the right-hand side, I have minus cosine x sine x. These two will subtract off, leaving us with the negative cosine x natural log secant x tangent x. This gives us our particular solution right there. If you need the general solution, you can add your complementary solution and your particular solution together, and you have it. Let's take a look at a slightly different setup. This will be the last example we look at. Then I'm going to do a quick review, and that'll finish out this video. Let's say we have this function xy double prime minus 1 plus xy prime plus y equals x squared e to the 2x, and we're going to assume, as is often the case, x is greater than 0. In this case, we start out being given our solutions to the homogeneous equation, 1 plus x and e to the x, and you're asked to prove or verify that these truly are solutions to the, notice, homogeneous equation, which means that we're going to start with our equation at the top of the screen, and on the right-hand side, instead of having the x squared e to the 2x, we're going to have equals 0. Okay, so let's see here. Let's first start with y1 equals 1 plus x. Easy enough to compute the derivative. The derivative is 1, and the second derivative is 0. Okay, so if I take these values for y prime, and y double prime, and substitute them into my equation, the homogeneous equation, okay, xy double prime, and you can read the rest of it, we're going to have x times the second derivative is 0, minus 1 plus x times y prime is 1, okay, plus y, and y is just 1 plus x. If you notice here, I have minus 1 plus x plus 1 plus x. Those are going to subtract off, and sure enough, that is a solution to the homogeneous equation. So that means 1 plus x works. We're also provided a second proposed solution to this differential equation, and that is that y2 is equal to e to the x. Well, it's pretty straightforward to compute the derivative and the second derivative of this. And as we did in the previous part A here, we're going to take and substitute, looks like e to the x in for y double prime, y prime, and y. And if you simplify that, you'll find that once again, it truly is equal to 0, which means that y2 equals e to the x is a solution. This gives us then our complementary solution, C1 times 1 plus x plus C2 times e to the x. This gives us kind of a head start on computing the particular solution. We already know our y1 and our y2. All we had to do is check and make sure that, yeah, that really works. Okay, so where do we go from here? We need to solve the non-homogeneous equation with the right-hand side equal to the x squared e to the 2x. Well, that x squared e to the 2x wasn't exactly one of those special cases on the method of undetermined coefficients. Okay, so we can use variation of parameters here. Right. So on to the second part, using the method of Lagrange or variation of parameters. We're going to have our x y double prime minus 1 plus x y prime plus y equals x squared e to the 2x. Then we're going to have our y double prime. Oh, wait a minute, what's going on here? Where did this second equation come from? Well, remember, the first thing we need to do is to make sure that the coefficient, the lead coefficient, or the coefficient on the y double prime is 1. We don't have that right now. So what we need to do is we need to divide everything by x, and this is actually the equation we're going to be solving. This has a 1 as the coefficient on y double prime. Aha. So what we're going to do now is we're going to use our system of equations that we are becoming familiar with here for the variation of parameters. We have our u1 prime y1 plus u2 prime y2 equals 0. In the first equation, we're going to substitute in 1 plus x for y1, e to the x for y2, and there's our first equation. Our second equation is going to be u1 prime times y1 prime. Now remember, y1 is this 1 plus x all the way up here in the left-hand corner. This time we want its derivative. Well, the derivative is just 1, and you see it there. For the second term, we want u2 prime times y2 prime. Well, our y2 is this e to the x. Its derivative is going to be e to the x, and you can see that right there. And now on the right-hand side, we have our x squared e to the x. Okay, so that gives us that. Let me correct that. It shouldn't be x squared, it should be x, because remember we had to divide everything by x up here. Okay, so that's x e to the 2x. We're going to take and we're going to subtract the second equation from the first one. Now you have to be kind of careful here, because what winds up being the case is in the first equation we have this u1 prime times 1 plus u1 prime times x. Our second term, we've got our u2 prime e to the x. Those will subtract off. That's pretty straightforward. But on our first term, remember, we really have two terms going on here. We have our u1 prime times 1. That'll subtract off with this. And we're left with a u1 prime times x. Right there it is. At this point, we can divide by x. And we're going to get u1 prime is equal to a negative e to the 2x, which gives us u1 is a negative 1/2 e to the 2x. Okay. Now remember, this is my u1. In order to compute u2, I'm now going to take and I'm going to substitute my u1, or my u1 prime, into the homogeneous equation that we're working with here in step 2. My u1 prime is going to be this negative e to the 2x times 1 plus x. Then I'm still going to have my u2 prime e to the x. Distributing out this e to the negative 2x over the 1 and the x gives me those two terms. Okay, I want to now solve this equal to 0. Well, I'm going to first add the e to the 2x to both sides. Cancels on the left, and I've got an e to the 2x on the right side. Same thing for the x, e to the x. So what we now have is u2 prime e to the x equals e to the 2x plus x e to the 2x. Be careful that the e to the x's do not cancel out. Notice the exponents. And what we're going to wind up with is e to the 2x divided by e to the x. That simplifies to be e to the x. We're going to have x e to the 2x divided by e to the x, which simplifies to give us x e to the x. To get u2, I need to integrate each of these terms. Well, the good news is e to the x can be integrated. That's e to the x. X e to the x can be integrated. That should bring back memories of integration by parts. Okay, and when you do the integration by parts here, you're going to get x e to the x minus e to the x, okay, from integrating that. Okay. Now you may be thinking, well, wait a minute, I forget, how does integration by parts work anyway? I'll run through it real quick like here. We have our integral x e to the x dx. We're going to set u equal to x. dv is going to be our e to the x dx. This means v, you have to integrate e to the x. Oh, that's just e to the x. We need du. Well, that's the derivative of x, which is just 1 dx. So this integral is going to be u times v. Well, that's x times e to the x minus the integral v, well, that's e to the x du, which is just dx. All right. We have our x e to the x minus, now we're going to do the integral of e to the x, which is e to the x. And sure enough, look at there. Right there it is. Okay, so just in case you needed a quick warm up there on integration by parts, that's how that works out. Now, we have these three terms. The e to the x's will subtract off, leaving us with u2. Remember, way over here on the left side, this is u2 is equal to x e to the x. Okay, now our particular solution is u1 y1 plus u2 y2. Well, our u1 that we obtained, it's up at the top of the screen, is the negative 1/2 e to the 2x times y1, which was given to us is 1 plus x, plus our u2, which is this x e to the x right there, times our y2, which was also given to us, e to the x. And that's got that one. So there is our particular solution. What you can do then is you can distribute out this negative 1/2 e to the x times the 1 and the x. When you do that, okay, what you're going to have is a negative 1/2 e to the x minus 1/2 x e to the 2x. Now, over here on the far right, when you multiply these together, you're going to get x e to the 2x. Remember, you add the exponents. Okay, so this will clean up a little bit. Let's see, we have our minus 1/2 e to the 2x. Well, that's not going to go anywhere because there's nothing to combine with that. But notice these two terms. They both have factors of x e to the 2x. We have one of them minus a half of one of them, which will give us 1/2 x e to the 2x. And there is the simplified version of the particular solution for that problem. Let's do a quick review here. See if we can sort things out. First thing, good news is most real-world situations involve at most a second-order differential equation. We have talked about higher-order differential equations. That's not going to be the majority of the situations that you see. You can run into two situations. You can get a non-homogeneous equation or a homogeneous equation. Notice in either case, the coefficient on the y squared term is 1. Now, my p, my q, and g, all three of those functions may or may not involve x. They may just be constants. If they are, method of undetermined coefficients is a good option. Okay? If P, Q, and G involve x and it's getting messy, you may want to think about is the g of x a special case that you can continue to use the method of undetermined coefficients, or do we need to use variation of parameter? It's your call. Now, if y1 is a homogeneous solution, you can compute another solution in the form y2 is equal to some function times y1, okay, which is a possibility, okay? You can use reduction of order to get this down to a second order equation. All right, really important. Point number 2 in the review. y1 and y2 form a fundamental solution of the homogeneous if and only if. That means this runs both ways. What this says is they're a fundamental solution if the Wronskian is not 0. And you can put it in reverse and say if the Wronskian is not 0, it forms a fundamental solution. This IFF, you may or may not have seen this before, means if and only if. So that's a two-way street. Okay, the general solution to the homogeneous, okay, or the complementary solution, if you want to call it that, is going to be C1y1 plus C2y2. Third thing to keep in mind, for any second order with constant coefficients, and remember this only works for constant coefficients, you can compute y1 and y2 of the homogeneous equation by using the quadratic formula and applying the appropriate case. Remember, the three cases are two roots, a double root, or two complex roots. Okay. The general solution of the non-homogeneous is going to be our complementary solution plus our particular solution. The particular solution being derived by things like the method of undetermined coefficients or this variation of parameters. Oh wait, here it is. It's option or point number 4. To get this, okay, talked about it a whole bunch already. To get the particular solution, this is if you have constant coefficients and a special right-hand side. I know I'm repeating this several times. Okay, that means this is important to remember. It doesn't mean I'm lost. Okay, if you have a special right-hand side and constant coefficients, use your method of undetermined coefficients. Okay. If you have a situation where you have a solution and a right-hand side that's not one of those special right-hand sides referred to in part 1 here, first make sure that the coefficient on y1 or y double prime is 1 and use this method of variation of parameters, which we just took a look at. I hope this is useful. You may wind up needing to go back through it a couple of times, I suspect, to root through. There's a whole lot of work that we've gone through in this. I wish you the very best with it. There's a whole lot here. I'm trying to get you all the way back up to the top.